Tonight, we're going somewhere cold. Not just cold the way a winter morning feels when you step outside and the air bites at your face, or cold the way a glass of ice water feels in your hand on a summer afternoon, or even cold the way the deep ocean feels, pressing in from all sides in the darkness far below where sunlight reaches. Those kinds of cold are real, but they're mild. They're familiar. They're things your body knows. The cold we're talking about tonight is something else entirely. We're talking about cold that exists on a scale so vast and so profound that the human mind can barely hold the edges of it. Cold that turns the very behavior of matter inside out. Cold that makes the universe reveal secrets it keeps hidden under ordinary conditions. Cold that sits so close to the absolute floor of all possible temperatures that even the energy of empty space itself, the faint, invisible hum of the cosmos, can no longer reach it. We're going to visit the coldest places in the entire universe, and what you'll find as we journey through them is something that might surprise you. Because cold is not simply the absence of heat. It is not just emptiness or silence or nothingness, even though it can feel that way. Cold, at these extremes, becomes something almost alive. It shapes the structure of reality. It births new forms of matter that shouldn't exist under normal conditions. It preserves ancient light and carries it across billions of years to reach us here. It will eventually, in the unimaginably distant future, define the final state of everything that exists. Cold, in other words, is one of the most profound and mysterious forces in the cosmos, and tonight you are going to drift through it. So take a long, slow breath. Let the air fill your lungs and then release it gently. There's nothing you need to do right now, nowhere you need to be, no decision that needs making. The only thing happening tonight is this: you resting, and the universe unfolding around you, vast and cold and endlessly beautiful. Let's begin where it always helps to begin, with the question of what cold actually is. Because to understand the coldest places in the universe, you first need to understand what temperature really means, and what it means for a place to be as cold as it is possible to be. And the answer, when you look at it closely, is one of the most elegant and strange ideas in all of physics. Temperature is motion. That's the simplest way to say it. When something is hot, the atoms and molecules inside it are vibrating and bouncing and spinning and colliding at tremendous speed. When something is cold, that motion has slowed. When something is very, very cold, that motion has slowed to a crawl. And cold means, in the deepest physical sense, that there is very little energy left in the system to extract. Your hand right now, if you were to place it on a cool countertop, is not really touching cold. You're losing heat. The energy in your hand is flowing outward into the surface, because the surface has less thermal energy than you do. Cold is a direction of flow. It is energy moving from a place of more to a place of less. And what we call feeling cold is really your body registering the departure of its own heat into something around it. Now, keep that idea, temperature as motion, as energy, because it becomes the key to understanding everything we're about to explore. Tonight, we are going to places where the energy has drained away so completely that it is almost impossible to comprehend. We are going to places where atoms barely move at all, where the quantum nature of matter itself begins to take over, because the laws that govern the small and strange world of quantum physics only become visible when ordinary thermal chaos has been stripped away. We are going to the places where the universe is most still, most quiet, most cold, and there is something about that stillness, that extraordinary quiet, that feels right for a night like this. As your breathing continues to slow, and your thoughts begin to thin out like mist on a warming morning, let the journey begin. We'll start with what temperature means at its absolute floor. Then we'll rise up through the cosmos, visiting the most frigid places we know of, natural wonders of cold scattered across the universe, before arriving at the far, far future where the ultimate cold of the universe's final state waits, patient and inevitable in the dark. There is nowhere warmer you need to be right now. You are here. That's enough. There is a temperature so cold that nothing in the universe can be colder. A number, precise and final, below which physics itself says, stop, no further, this is the end. That temperature is called absolute zero, and it is defined as zero on the Kelvin scale, which corresponds to negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. It is the point at which, in theory, all thermal motion ceases. At absolute zero, atoms would stop vibrating. The random, chaotic dance of particles that we call heat, that restless, jostling motion that never fully stops under ordinary circumstances, would in principle come to rest. In principle. Because here is the extraordinary thing. Absolute zero cannot actually be reached. Not by any process in the physical universe, not by any amount of cooling, however clever or extreme. It is the ultimate limit, the asymptote at the end of the temperature axis, which you can approach forever but never quite touch. This isn't simply a practical limitation, a matter of our technology not being good enough yet. It is written into the deepest laws of thermodynamics, the physical laws that govern energy and entropy. The third law of thermodynamics states that the entropy, the disorder of a system, approaches a constant minimum as temperature approaches zero, and that it takes an infinite number of steps to actually get there. No finite series of cooling procedures can ever arrive at absolute zero. The floor is real, but you can never quite stand on it, and yet this impossible floor has shaped our understanding of the universe in profound ways. The Kelvin scale, named after the Scottish physicist William Thomson, who later became Lord Kelvin, was established in the mid-1800s precisely because scientists needed a temperature scale that started at this absolute floor rather than an arbitrary reference point like the freezing of water. Celsius and Fahrenheit are fine for everyday life, but science needed a scale that spoke the deeper language of energy. The Kelvin scale does exactly that. 0 Kelvin is not just a very cold temperature. It is the complete absence of thermal energy. It is physical silence. Everything in the universe exists somewhere above this floor. Ordinary room temperature is about 293 Kelvin. The surface of the Sun is around 5,778 Kelvin. The core of the Sun reaches about 15 million Kelvin. And on the cold end, well, the average temperature of the universe as a whole, that faint background hum of leftover energy from the Big Bang, is about 2.725 Kelvin, just 2.725 degrees above absolute zero. The universe we live in is, taken as a whole, extraordinarily cold already. We exist in a warm bubble, a solar system bathed in the heat of a star, but surrounding us in every direction is a universe hovering barely above the theoretical floor of all possible temperatures. Now, what happens as you get very, very close to absolute zero? This is where things become beautiful and strange. At extremely low temperatures, matter begins to behave in ways that simply do not happen under ordinary conditions. The quantum mechanical nature of particles, which is normally hidden beneath the chaos of ordinary thermal motion, begins to reveal itself. Particles lose their individual identities and begin to behave collectively, as if they are one, single entity rather than a collection of separate atoms. One of the most spectacular of these phenomena is called a Bose-Einstein condensate. It was predicted mathematically in 1924 and 1925 by the Indian physicists Satyendranath Bose and Albert Einstein, who showed that under the right conditions at temperatures approaching absolute zero, certain types of particles would collapse into a single, shared quantum state. They would stop being individual particles and become a kind of superatom, a collection of atoms all behaving identically, all in the same quantum state at the same moment. It took 70 years to actually create this in a laboratory. In 1995, physicists Eric Cornell and Carl Wieman at the University of Colorado, working with a team at GILA, managed to cool a cloud of rubidium atoms to a temperature of about 170 billionths of a degree above absolute zero. At that point, the atoms condensed into the world's first Bose-Einstein condensate. The achievement won them the Nobel Prize in Physics in 2001, shared with Wolfgang Kettel of MIT, who created his own Bose-Einstein condensates shortly after using sodium atoms. Bose-Einstein condensates are extraordinary things. In this state, atoms move so slowly that it takes them half a minute just to cross a single inch of space. In an ordinary gas at room temperature, the same atoms would move at nearly the speed of a jet airplane. The Bose-Einstein condensate exists in a kind of profound quantum stillness that is unlike anything in ordinary matter. But the quest to approach absolute zero didn't stop there. In 2003, Wolfgang Kettel's team at MIT pushed the record further, cooling a gas of sodium molecules to just 500 picokelvin, that is 500 trillionths of a degree above absolute zero. This broke the previous record by a factor of 6 and remains one of the most astonishing feats of experimental physics ever achieved. Then in 2021, a team of German scientists at Leibniz University in Hanover pushed the boundary even further. They placed 100,000 rubidium atoms in a magnetic trap at the top of the University of Bremen's 110-meter drop tower. When they released the trap and allowed the atoms to fall freely through the tower in a state of near weightlessness that lasted for just under 5 seconds, while simultaneously pulsing the magnetic field on and off to slow the atom's expansion, they achieved an effective temperature of just 38 picokelvin, that is 38 trillionths of a degree above absolute zero. The record lasted for only 2 seconds, but it happened. The coldest things human beings have ever created are things that no natural place in the universe can match. Not the Boomerang Nebula, about which we'll speak at length in just a moment. Not the empty void between galaxy clusters. Not the shadowed craters of distant moons. The coldest places in the known universe, at least for a few precious seconds, have been small metal chambers on Earth, in laboratories filled with careful, patient scientists who have dedicated their careers to the art of making things incredibly still. There is something wonderful about that. The hottest temperatures in the universe, the cores of massive stars, the split-second inferno of the Big Bang, are beyond anything we can create in a lab. But the coldest, we can get closer. We can nudge ourselves right up to the floor. We can sit within 38 trillionths of a degree of the bottom of the thermodynamic scale. The universe's ultimate cold is something we've nearly touched with our own hands. As you let that sink in, let your own body relax into whatever surface it rests on. You, right now, are radiating heat into the world around you. Your body temperature of around 310 Kelvin, 37 degrees Celsius, is a kind of warmth that took billions of years of stellar evolution to make possible. The iron in your blood was forged in the heart of a dying star. The atoms in your body vibrate with a thermal energy that ties you to the vast cosmic dance. But even that warmth is small and brief in the grand scale of things. The universe around us is cold, and the colder it gets, the stranger and more beautiful the things that happen within it. Let's go somewhere cold now. Somewhere very, very cold. A place 5,000 light-years away that holds a record no natural object in the known cosmos has ever beaten. Picture a place in space shaped like the ghost of a butterfly, 2 great curved lobes of gas and dust stretching outward from a dying star at their centre. Pale and luminous in the light of a star it can no longer fully illuminate. This is the Boomerang Nebula, and it is the coldest known natural place in the entire observable universe. It sits approximately 5,000 light-years from Earth, in the direction of the southern constellation Centaurus. It was first discovered in the late 1970s, glimpsed through ground-based telescopes by astronomers S. Glass and G. Wegener at the South African Astronomical Observatory. They noted its unusual shape, a kind of bow tie or butterfly formation, asymmetrical and strange. Then in 1980, astronomers Keith Taylor and Mike Scarrett made their own observations using the Anglo-Australian telescope at Siding Spring Observatory, and gave it the name we still use today, the Boomerang, because its curved, lopsided shape reminded them of the throwing stick. But it wasn't until 1995 that the full significance of this nebula became clear. That year, astronomers Raghavendra Sahai of the Jet Propulsion Laboratory and Lars-Åke Nyman of the European Southern Observatory used the 15-meter Swedish ESO submillimeter telescope in Chile to study the nebula in detail. What they discovered shocked the scientific community. The Boomerang Nebula was colder than the background temperature of space itself. It was colder than the cosmic microwave background radiation, the faint glow left over from the Big Bang that permeates every cubic centimetre of the universe. It was, as far as anyone had ever measured, the coldest natural place in the universe. The temperature at the heart of the Boomerang Nebula is approximately 1 Kelvin, 1 degree above absolute zero. In Celsius, that is negative 272 degrees. In Fahrenheit, it is negative 458 degrees. The cosmic microwave background, the coldest thing that most of the universe settles to, the minimum baseline temperature of open space, is 2.725 Kelvin. The Boomerang Nebula is colder than that. It is the only known natural object in the universe that is colder than the ambient background glow of the cosmos. To put that in perspective, the coldest place on Earth is somewhere in Antarctica, where surface temperatures have been measured as low as -98 degrees Celsius. That is about 175 Kelvin. The Moon's dark side, in permanent shadow, reaches about 100 Kelvin. The space between stars is typically at the temperature of the cosmic microwave background, roughly 2.725 Kelvin, and then, beneath all of that, alone in its extraordinary frigidity, the Boomerang Nebula sits at 1 Kelvin, colder than the rest of the universe's natural background. So what is actually happening there? Why is this particular nebula so extraordinarily cold? The answer lies in what the Boomerang Nebula actually is, a dying star, and the extraordinary violence of its death. The Boomerang Nebula is classified as a pre-planetary nebula, an object in the brief transitional phase of stellar evolution between the asymptotic giant branch stage and the planetary nebula stage. Its central star is an old, evolved star, likely once similar to our own Sun, that has reached the end of its nuclear burning life. As it aged, it entered its giant phase, swelling outward and beginning to shed its outer layers. This kind of mass loss is common in aging stars. But what makes the Boomerang Nebula unique is the rate at which this is happening, and the speed at which the ejected material is moving. The star at the centre of the Boomerang Nebula has been losing mass at a rate of roughly 1,000th of a solar mass per year. That number might not sound enormous, but it is 10 to 100 times more mass loss than any other similar object ever observed. And it has been doing this for approximately 1,500 years. Over that time, it has ejected an amount of material roughly equivalent to 1.5 times the mass of our entire Sun, and that material is moving fast. The gas flowing outward from the dying star is moving at a velocity of about 164 kilometers per second. That is nearly 370,000 miles per hour, more than 590,000 kilometers per hour. This is a fierce, violent wind streaming outward from the star at breakneck speed. Now here is where the physics becomes beautiful. When a gas expands rapidly, when it is allowed to flow outward into a larger volume, it cools. This is the same principle that makes an aerosol spray feel cold when you press the button and release gas from a pressurized can. The gas expands. The expansion converts internal energy into motion, and as a result, the temperature drops dramatically. In the Boomerang Nebula, this process is happening on a cosmic scale. The gas is being ejected so fast and expanding so rapidly into the surrounding space that it cools to a temperature below even the cosmic microwave background radiation. It has become its own cosmic refrigerator. Sahai himself described it that way, a natural refrigeration system driven by the dying exhalation of a star. The discovery was confirmed and extended by later observations, including a remarkable set of images taken by the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile. ALMA can observe the nebula in radio wavelengths, and those observations revealed that the true shape of the Boomerang Nebula is not the simple hourglass that Hubble's visible light images showed, but rather something far more complex and diffuse. A roughly spherical outer envelope of cold, expanding gas surrounds the more structured inner hourglass. The real nebula is larger and stranger than early images suggested. The ALMA observations also confirmed the extraordinarily cold temperature of the outer gas, 1 Kelvin, as cold as anything in nature has ever been measured. The gas absorbs the cosmic microwave background radiation, rather than being warmed by it, which is how astronomers were able to determine its temperature. The microwave background is more energetic than the Boomerang's cold gas, so the gas absorbs energy from the background rather than emitting it, making the nebula appear as an absorption feature rather than an emission feature at those wavelengths. This is how you measure the temperature of something colder than space itself. You watch it drink in the warmth of the universe around it. There is something that might strike you as almost poignant about the Boomerang Nebula. Here is a star at the end of its life, aging, swelling, losing its substance to the surrounding space, and in that process of loss, in that long, gentle exhalation of gas and dust into the dark, it creates something extraordinary. A cold so profound that no natural process in the known universe has surpassed it. The dying star becomes the coldest thing in the cosmos. The Boomerang Nebula is also changing. Astronomers believe that as the nebula ages, as the expansion slows and the gas spreads thinner across a larger volume, it will gradually warm toward the background temperature of the universe. The extraordinary cold of its current phase is temporary, a brief, exceptional moment in the long life of a stellar system. Eventually, the central star will shed its last layers, the nebula will fully develop, and the cold core will warm back to the ambient temperature of space. The record may one day be reclaimed by the universe around it, but for now, for this moment in cosmic time, the Boomerang Nebula holds the title, the coldest natural place in the universe, a fading star's last frigid breath. Let your own breathing slow, like that gentle, slow exhalation of gas into the dark. The Boomerang Nebula is drifting through the constellation Centaurus at this very moment, invisible to the naked eye, unreachably distant, yet mapped in its every detail by the patient instruments of science. A cloud of cold so extreme that it absorbs the warmth of space itself. Beyond the Boomerang Nebula, scattered across the galaxy in vast dark formations that stretch for hundreds of light years, there are places of extraordinary cold that are perhaps more familiar in their purpose, even if not in their scale. These are the molecular clouds, the enormous frigid reservoirs of gas and dust from which all the stars in the universe are born. Molecular clouds are among the largest structures in any galaxy. Some of the biggest ones in the Milky Way, called giant molecular clouds, can stretch for 150 to 200 light-years across and contain enough material, mostly hydrogen molecules, to form tens of thousands of stars. They are not uniform structures. Inside, they have dense cores and thin edges, filaments and clumps, regions of higher and lower density shaped by gravity and the slow turbulence of galactic forces over millions of years, and they are cold, extraordinarily cold by any earthly standard, though not quite as cold as the Boomerang Nebula. The temperature in the interior of a typical molecular cloud ranges from about 10 to 30 Kelvin. That is, between -263 and -243 degrees Celsius. In the densest cores, where the gas is most concentrated and the surrounding material blocks even the faint warmth of background starlight, temperatures can dip toward the lower end of that range. 10 Kelvin is 10 degrees above absolute zero, about 8 times warmer than the Boomerang Nebula, but still incomprehensibly cold by any measure that relates to our everyday experience. These places are cold because they are shielded. In the outer regions of a molecular cloud, ultraviolet light from nearby stars can penetrate and heat the gas, dissociating the hydrogen molecules and warming the material. But deeper in, the layers of dust act as a shield, blocking that light and allowing the temperature to fall toward its minimum value. The dust itself, microscopic grains of carbon, silicates, and ices, absorbs any incoming radiation and re-emits it at longer wavelengths, further reducing the energy available to heat the gas. The interior of a dense molecular cloud core is one of the most thermally isolated environments in the galaxy. It is in precisely these cold, dense regions, these frigid cores within the larger clouds, that the first steps of star formation take place. Gravity works slowly in these places, gathering molecules into clumps, drawing slightly denser regions together until, over hundreds of thousands of years, a core collapses under its own weight. The material falls inward, heating as it compresses until the temperature at the center reaches the millions of degrees needed for nuclear fusion to ignite. And just like that, a star is born. The coldest places in the galaxy become the birthplaces of suns. It is one of the most beautiful paradoxes in all of astrophysics. The cold is not the absence of creation. The cold is the necessary precondition for it. The temperature must be low enough for the gas to settle and condense, low enough for the molecular hydrogen to remain stable, low enough for gravity to gain the upper hand over thermal pressure. Too much heat, and the gas simply expands and dissipates into the interstellar medium, never coalescing into anything. The stars we see shining in the night sky, every single one of them, were born in cold, dark, frigid molecular clouds much like these. Your own sun was born in such a cloud some 4.6 billion years ago. The solar system condensed from a region of cold, dense molecular gas in what is now the Milky Way. The oxygen you breathe, the iron in your blood, the calcium in your bones, all of it was processed through stars that in turn were born in cold molecular clouds. The cold nurseries of the cosmos are the ancestors of life itself. Some of the most famous molecular clouds visible from Earth are sites of active star formation you might know by name. The Great Orion Nebula, that fuzzy spot in the sword of the constellation Orion, visible to the naked eye on a clear night, is the bright glowing inner face of an enormous molecular cloud complex that stretches across much of the constellation. The glowing part, illuminated by the ultraviolet light of young, massive stars recently born within it, is just the lit edge of a much larger cold, dark structure behind it. The dark molecular cloud itself doesn't glow. It absorbs light. It is cold and invisible in the visible spectrum, detectable only to radio and infrared telescopes that can peer through its depths. The Orion Molecular Cloud complex is one of the most studied star-forming regions in the galaxy. It contains dense cores in various stages of collapse, protostars just beginning to gather their material, full young stars still surrounded by the disks of gas and dust that will eventually become planetary systems, and more mature young stars that have blown bubbles in the surrounding gas with their energetic light and stellar winds. It is a region of cold punctuated by blazing new fires, dark and quiet in the molecular interior, brilliant and violent at the edges where new suns ignite. And while the Orion Nebula is perhaps the most famous, it is only one of many such nurseries scattered across the Milky Way. The Carina Nebula, the Eagle Nebula, home to the famous Pillars of Creation photographed by the Hubble Space Telescope. The Trifid Nebula, the Lagoon Nebula. All of these are regions where molecular clouds give birth to stars, where cold and dark give way to heat and light, where the long, slow patience of gravity finally wins. What's remarkable is the chemistry that happens in these cold clouds. At temperatures of 10 to 30 Kelvin, molecules form and survive in ways they couldn't in warmer environments. Simple molecules like carbon monoxide and water ice are stable in the cold, but more complex molecules form too. Polycyclic aromatic hydrocarbons, formaldehyde, methanol, glycolaldehyde, a simple sugar, and even amino acids have been detected in molecular clouds. The cold allows these complex chemical structures to persist without being immediately torn apart by thermal energy. This means that the molecular clouds are not just cold nurseries for stars, they are cold laboratories for chemistry, places where the organic building blocks of life can form and persist, waiting to be incorporated into the gas and dust disks surrounding newly forming stars, waiting to be swept up into comets and asteroids and eventually into the surfaces of young rocky planets. The cold, in other words, preserves possibility. It holds the ingredients of life in suspension, waiting for the warmth of a new sun to set them in motion. As you drift a little further into rest right now, imagine those cold, dark cloud cores scattered across the galaxy, quiet and still and barely warmer than absolute zero, slowly gathering themselves under gravity's patient hand. Each one a story not yet begun, each one a future star, a future solar system, perhaps a future world. The cold is the waiting, the cold is the potential. And from that potential, everything warm comes. If you could feel the temperature of the universe itself, not the temperature near a star or a nebula or a hot gas cloud, but the baseline temperature of empty space, the ambient background of the cosmos as a whole, you would feel something extraordinarily cold. Not as cold as the Boomerang Nebula, not as cold as the molecular cloud cores, but colder than anything on Earth, colder than the coldest night in Antarctica, colder than the shadowed side of Pluto. The universe itself, taken in its entirety, has a temperature of 2.725 Kelvin. That is the temperature of the cosmic microwave background radiation, the CMB, the ancient faint glow that fills every corner of the observable universe, streaming in from every direction equally, a perfect bath of microwave photons left over from the earliest moments of cosmic history. To understand this extraordinary thing, you need to travel back in time, not just back centuries or millennia or even millions of years, but back to the very beginning, to the first few 100,000 years after the Big Bang. In the beginning, or at least in the earliest moments we can meaningfully talk about, the universe was nothing like it is today. There were no stars, no galaxies, no planets, no empty space in the way we understand it. The universe was a hot, dense, opaque soup of matter and energy. Protons and electrons were too energetic to combine into atoms. Photons, particles of light, couldn't travel freely because they were constantly bouncing off the free electrons surrounding them. The entire universe was a glowing, opaque fog, roughly as transparent as the interior of the sun. This went on for about 380,000 years. Then, as the universe expanded and cooled, as it stretched and diluted its own heat across an ever larger volume of space, the temperature dropped to about 3,000 Kelvin, At that temperature, something remarkable happened. The electrons finally slowed down enough to be captured by the protons, forming the first neutral hydrogen atoms. The fog lifted. The photons that had been bouncing around, trapped in that hot plasma, were suddenly free to travel. They streamed outward in every direction, filling the universe with light. That flash of light, the first freely travelling radiation in the history of the universe, is what we now detect as the cosmic microwave background. Those original photons have been travelling ever since. They have been stretched, redshifted, by the expansion of the universe over the past 13.8 billion years, losing energy and cooling as the universe around them grew. When they were first emitted, they corresponded to a temperature of 3000 Kelvin. Today, after 13.8 billion years of expansion, they correspond to a temperature of just 2.725 Kelvin. The cosmic microwave background is the afterglow of the Big Bang, cooled by the expansion of the universe from a blinding hot plasma glow to a faint whisper of microwave radiation almost below the threshold of detection. It is, in a sense, the oldest light in the universe, the most ancient signal that can ever reach us with electromagnetic radiation. Everything before the CMB is hidden behind that opaque veil of the early plasma. The CMB is our cosmological horizon. It is as far back in time as light can reach us. This light was first accidentally discovered in 1964 by two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson. They had built a large microwave antenna designed to communicate with early communication satellites. No matter what they did, no matter how carefully they calibrated their equipment, they detected a persistent hiss, a steady background noise coming from every direction of the sky equally. They went so far as to clean out a pair of pigeons that had roosted in the antenna horn and left their droppings behind, thinking the birds might be the source of the interference. The hiss persisted. Eventually they made contact with cosmologists at Princeton who were actually searching for this signal, and the two groups realized they were looking at, or rather listening to, the relic radiation from the Big Bang. Penzias and Wilson shared the 1978 Nobel Prize in Physics for the discovery. What makes the CMB so scientifically precious is not just its existence, though that alone is extraordinary, but its fine details. When you look at it with exquisitely sensitive instruments, the CMB is not perfectly uniform. There are tiny temperature fluctuations, variations of just a few hundred thousandths of a degree, from one point in the sky to another. These minuscule ripples in the temperature of the CMB are the echoes of density fluctuations in the early universe, regions that were very slightly denser than average, and regions that were very slightly less dense. The denser regions warmed the photons passing through them slightly. The less dense regions cooled them slightly. Those temperature differences were imprinted on the light at the moment of decoupling, 380,000 years after the Big Bang. And those density fluctuations in the early universe, those tiny ripples in the primordial soup, are the seeds from which all the large-scale structure of the cosmos grew. The slightly denser regions attracted more matter over billions of years, growing into filaments of galaxies, into galaxy clusters and superclusters. The less dense regions became the great cosmic voids, vast empty expanses of space that contain almost nothing at all, which we'll explore in the next section. Every galaxy you have ever seen in an image from Hubble or Webb, every star in the Milky Way, every planet in every solar system, all of it traces its origin to those microscopic temperature variations in the CMB. The first satellite dedicated to mapping the CMB in detail was NASA's Cosmic Background Explorer, COBE, launched in 1989. It confirmed with precision that the CMB was extraordinarily uniform and also detected for the first time those tiny temperature fluctuations. Its principal scientists, John Mather and George Smoot, received the Nobel Prize in Physics in 2006. Then came the Wilkinson Microwave Anisotropy Probe, WMAP, which mapped the CMB in greater detail over the course of 9 years and helped establish the age of the universe as 13.77 billion years, determine the proportion of ordinary matter, and dark energy in the cosmos, and measure the overall geometry of the universe as very close to flat. Most recently, ESA's Planck satellite made the most precise maps of the CMB ever produced, measuring temperature fluctuations to better than a millionth of a degree. What these missions revealed collectively is a universe that is remarkably uniform on large scales. That temperature of 2.725 Kelvin is consistent across the entire observable universe to within 1 part in 100,000, but which contains, encoded in those tiny fluctuations, the complete history of cosmic structure formation. The CMB is the universe's baby picture, a snapshot of the cosmos when it was just 380,000 years old, before there were any stars or galaxies, before there was any complex structure, just a cooling, expanding bath of photons carrying the imprints of the seeds of everything that would come, and it is cold, 2.725 Kelvin, negative 270 degrees Celsius. It is the temperature that space itself settles to, far from any source of heat. It is the reason that deep space, the emptiness between stars and galaxies, is not at absolute zero, but is instead hovering a few degrees above it. The CMB warms the void. It is the universe's own ambient temperature, the thermodynamic flaw left behind by its birth. As the universe continues to expand, this temperature continues to drop. Very slowly, almost imperceptibly on human timescales, but inexorably. In 1 trillion years, the CMB temperature will have dropped further still. The background radiation will have stretched to longer and longer wavelengths, cooled to lower and lower temperatures. Eventually, in the unimaginably distant future, it will approach absolute zero itself. But that is a story for later in our journey. For now, let the idea of the cosmic microwave background wash over you. Right now, this instant, microwave photons from the edge of the observable universe, photons that have been travelling for 13.8 billion years, photons that were released when the universe first became transparent, are passing through you. They are moving through the room you are resting in. They are passing through the walls, through the earth, through everything. Faint and ancient and cold, the oldest light in the universe, streaming silently through your body as you begin to drift towards sleep. The universe is not smooth. From a great enough distance, the structure of the cosmos looks something like a vast three-dimensional web, a cosmic foam of filaments and walls of galaxies, threaded through with enormous regions of almost nothing at all. These regions, these great empty expanses, are called cosmic voids, and they are among the coldest places in the universe, not because they contain anything extraordinarily frigid, but because they contain almost nothing at all. To understand voids, you need to understand the large-scale structure of the universe. After the Big Bang, the universe began with a distribution of matter that was very nearly uniform, but not quite. There were tiny quantum fluctuations, small variations in density that we see encoded in the cosmic microwave background. Over billions of years, gravity amplified these fluctuations. Regions of higher density attracted more matter, grew denser still, drew in gas from surrounding regions, and eventually formed the filaments and sheets of galaxies we see today. Regions of lower density lost their matter to the surrounding overdense structures, growing emptier and emptier over time. The result is the cosmic web, a vast foam-like structure in which essentially all the galaxies in the observable universe are concentrated in thin walls, sheets, and filaments surrounding enormous bubbles of near emptiness. The filaments and walls contain the matter. The bubbles are the voids. Voids are genuinely immense. The average cosmic void spans somewhere between 10 and 100 megaparsecs in diameter. That is between about 33 million and 330 million light years. To cross the average void at the speed of light would take tens of millions of years. To cross the largest known supervoids would take hundreds of millions of years. These are not merely large spaces. They are regions of the universe so vast that if you place the entire distance from Earth to the nearest star, Proxima Centauri, about 4.2 light-years away, at the edge of a void, it would be utterly invisible against the scale of the surrounding emptiness. And when we calculate the total volume of the universe that is made up of these voids, the number is staggering. Roughly 80% of the volume of the observable universe consists of these underdense regions. Most of the universe, by volume, is void. Most of the universe is nearly empty. The galaxies and stars and planets, all the luminous, bustling stuff that seems so impressive when we look at images from space telescopes, occupy only a small fraction of the universe's total volume. They are concentrated into thin walls around enormous, quiet, cold, dark, empty bubbles. The most famous cosmic void is the Bouters void. It was discovered in 1981 by astronomer Robert Kirshner of the University of Michigan during a survey of galaxy redshifts designed to create a three-dimensional map of the universe. When Kirshner and his colleagues plotted their data, they found a region of the sky in the direction of the constellation Boötes that was simply and shockingly empty. Where they expected to find hundreds of galaxies based on the average density of the universe, they found almost nothing. The Boötes void spans roughly 250 to 330 million light-years across. Its centre lies about 700 million light-years from Earth. It contains only about 60 known galaxies, where statistical expectation would place roughly 2,000 in that volume, and those 60 or so galaxies are arranged in a strange elongated tube-shaped distribution that runs through the middle of the void, as if the galaxies retreated to a corridor rather than filling the space evenly. The astronomer Greg Aldering famously remarked that if the Milky Way had been located in the centre of the Boötes void, we would not have known other galaxies existed until the 1960s, when our telescopes became powerful enough to see across the void to the galaxy walls beyond it. The nearest galaxies to us would have been unimaginably far away, and the night sky would have been essentially starless beyond our own galaxy. The Boötes void is large enough that some astronomers initially found it puzzling. Standard models of cosmic evolution suggested that voids of this size might take longer than the current age of the universe to form through the natural segregation of matter. The most widely accepted explanation today is that the Boötes void formed through the merging of several smaller voids as the universe evolved and galaxies were drawn away by gravity towards surrounding overdense structures. What is the temperature inside a cosmic void? There is no single, simple answer, because voids are not truly empty. They contain small amounts of gas, the occasional stray galaxy, and the omnipresent cosmic microwave background radiation. The ambient CMB temperature of 2.725 Kelvin pervades the void just as it pervades everywhere else. But voids do have a small but measurable effect on the CMB temperature, because of a phenomenon called the integrated Sachs-Wolf effect. As photons of the CMB pass through a void, the gravitational potential of the void can cause them to lose energy slightly. They climb in and then expand with the void, and if the void is growing due to the expansion of the universe, they come out slightly cooler than when they went in. This effect is subtle. The temperature differences are tiny, but it is one way that voids leave their imprints on the CMB. Regions of the CMB that appear slightly cooler than average tend to correspond to the presence of large voids along the line of sight. Astronomers can effectively map the large-scale distribution of voids by looking for cold spots in the microwave sky. Speaking of cold spots, there is a particularly famous one known simply as the CMB cold spot. It appears in the microwave sky in the direction of the constellation Eridanus, and it is considerably colder than its surroundings, about 70 microkelvin below the average, and larger than standard cosmological models would predict. It is one of the most discussed anomalies in cosmology. Some researchers have proposed that the cold spot is associated with an immense supervoid, a region of particularly low galaxy density about 150 megaparsecs across, lying between us and the CMB surface. The supervoid hypothesis would explain the cold spot through the integrated Sachs-Wolf effect, without requiring any exotic physics. Other explanations that have been proposed include the effects of cosmic textures, topological, defects from phase transitions in the early universe, collisions with other universes in a multiverse scenario, and various statistical flukes. The truth is that as of the current state of science, the cold spot remains an open mystery. It may be the most conspicuous evidence of a vast cold void stretching across hundreds of millions of light-years, or it may be something stranger still. The voids, whatever their ultimate nature, are a reminder that the universe is mostly made of nothing. The light and heat and complexity that we celebrate, the stars and galaxies and nebulae, are the decorations on the surface of a cosmic foam whose interior is dark and cold and nearly empty. The voids are not a flaw in the universe's design. They are a fundamental feature of how gravity works over cosmic time, separating matter into walls and leaving vast, cold emptiness between them. As you continue to drift, let the idea of those enormous empty bubbles settle into your imagination. Regions where a spacecraft could travel for tens of millions of years at the speed of light and encounter almost nothing. Regions where the only temperature is the ambient microwave glow of the universe itself, a cold so deep and even and ancient that it is almost like silence made into a temperature. In the voids, the universe simply waits, cold dark, and patient. Between the stars in the cold emptiness of interstellar space, there are worlds. Not worlds orbiting suns, receiving light and warmth that sustain weather and geology and perhaps even life. These are worlds with no sun at all, planets ejected from their home solar systems, or perhaps formed in the isolation of interstellar space, drifting forever in darkness and cold. They are called rogue planets, or free-floating planets, or orphan worlds, and they are among the most desolate and haunting places in the universe. The existence of rogue planets was suspected by astronomers long before they could be detected because the physics of planetary formation and gravitational dynamics essentially guarantees their existence. When planets form around a star, the process is chaotic. Young planetary systems are not orderly. They are dynamic, evolving collections of objects whose orbits interact and shift over time. Close encounters between planets can generate gravitational slingshots that fling smaller bodies onto highly eccentric orbits, and sometimes those orbits are energetic enough to escape the star's gravity entirely. The planet is kicked out of the system and begins its long journey through interstellar space. This is thought to have happened in our own solar system's early history. Computer simulations of the formation of the solar system suggest that a fifth giant planet may have once existed in the early solar system before being ejected by gravitational encounters with Jupiter, Saturn, Uranus, and Neptune. If that model is correct, our Sun created at least one rogue planet billions of years ago, and it is drifting somewhere in the galaxy right now. But rogue planets can also form independently, without ever having been part of a planetary system. They can form the same way stars do, from the gravitational collapse of a cloud of gas and dust, but the cloud is too small and lacks enough mass to ignite nuclear fusion and become a star. The result is a planet-sized body floating free in space, never having had a parent star, a planetary orphan by birth rather than by exile. Detecting rogue planets is extraordinarily difficult because they emit almost no light. Without a star to warm them, they are cold and dark. The main method scientists use to detect them is gravitational microlensing, watching for the brief characteristic brightening of a distant background star as a rogue planet passes in front of it, bending the star's light through gravity. The brightening lasts only hours to days, and the signal is difficult to distinguish from other kinds of microlensing, events. Despite the detection challenges, the results already suggest that rogue planets are extraordinarily common. Statistical analyses of microlensing surveys have suggested that the Milky Way may contain hundreds of billions of rogue planets, possibly more than the number of stars in the galaxy. Some estimates push the number even higher, to trillions. Rogue planets may be the most numerous type of planet-sized object in the universe, even though we can barely detect them at all. What is it like on a rogue planet? Imagine a world with no sun, no day, no seasons, no sunlight touching the surface, ever. The sky, if you could stand on the surface, would be eternal night, a view of the stars and very faintly the band of the Milky Way, but no daylight, no solar warmth, no photosynthesis, no obvious energy source for any surface life as we know it. The surface temperature of a rogue planet, in the absence of any internal heat source, would approach the ambient temperature of the space around it, approximately 2.725 Kelvin, the temperature of the cosmic microwave background. In more practical terms, temperatures would hover near negative 270 degrees Celsius, or negative 454 degrees Fahrenheit. Everything on the surface would be frozen solid. Any atmosphere would be frozen solid. Gases that on Earth exist as fluids or vapors, nitrogen, oxygen, carbon dioxide, would all be locked in frozen layers on the surface, or lost to space entirely over billions of years. Some rogue planets, however, retain internal heat from their formation. Planets form through the accretion of material, through collisions and impacts that release enormous amounts of energy in the form of heat. That heat takes time to dissipate. For large rogue planets, particularly those with masses several times that of Jupiter, the internal heat can be substantial enough to maintain temperatures far above absolute zero in the interior, and in some cases warm enough at depth to potentially maintain liquid water beneath the surface. One of the most intriguing nearby rogue planets is an object designated WISE 0855-0714, located just over 7 light-years from Earth, making it one of the closest known planetary mass objects beyond the solar system. It was discovered using NASA's Wide Field Infrared Survey Explorer telescope, which detected its faint infrared glow. Its surface temperature is estimated at around -48 degrees Celsius, cold by human standards, comparable to the most frigid regions of Earth's polar environments, but extraordinarily warm for a free-floating object in interstellar space. Its warmth likely comes from residual internal heat from its formation. Intriguingly, spectroscopic observations have suggested the presence of water clouds in its atmosphere, the first such clouds detected on a planetary mass object outside our solar system. The possibility of life on rogue planets, underground life, sustained by geothermal heat rather than sunlight, is a fascinating subject of scientific speculation. In 1998, physicist David Stevenson of Caltech proposed that certain types of rogue planets could retain thick hydrogen atmospheres that would act as powerful thermal blankets, trapping internal heat and potentially keeping a subsurface layer of water liquid. A rogue planet with enough internal heat, the right mass, and a thick enough hydrogen atmosphere could theoretically maintain liquid water deep beneath its surface for billions of years. And where there is liquid water and a chemical energy source, such as the heat from hydrothermal vents, there might be the conditions for life. We know that on Earth, life exists in deep-sea hydrothermal vent communities that receive no sunlight whatsoever. These ecosystems are powered entirely by chemical energy from the Earth's interior, hydrogen sulfide and other compounds released by volcanic activity, metabolized by microorganisms that form the base of a food web. Such ecosystems, in principle, could exist on rogue planets too, deep beneath a frozen surface, powered by the slow leakage of internal heat. We don't know for certain whether life exists on rogue planets. We have never been able to study the surface or interior of one in any detail. But the possibility exists, and it is a remarkable one, that the universe may host life not only on planets orbiting warm suns, but on dark, wandering worlds, drifting alone through the cold of interstellar space, their interiors secretly warm, their surfaces encased in ice and darkness. The rogue planets drift on, invisible and cold, their surfaces frozen to near absolute zero, their numbers perhaps exceeding the stars. They are among the most abundant worlds in the galaxy and among the least known. Billions, perhaps trillions, of dark, frozen spheres moving silently through the cold between stars, carrying whatever secrets they have deep within themselves. Let that image settle over you as you drift toward rest. Somewhere out there, right now, a planet is drifting through the cold dark of space, its surface a frozen sheet of ice and frozen gas, its interior perhaps quietly warm, its sky a perpetual night scattered with distant stars. A world that has never seen a sunrise, a world that has always been alone. Stars do not die cleanly. When a star exhausts its nuclear fuel, when the long, slow burn of fusion that has sustained it for millions or billions of years finally sputters to an end, what remains is not nothing. The universe recycles. The corpses of stars continue to exist, changing, cooling, fading, for timescales that dwarf the current age of the cosmos. These stellar remnants come in several varieties, depending on the mass of the original star. Stars like our Sun, and all stars up to about 8 times the Sun's mass, end their lives by shedding their outer layers into space. A beautiful, slow explosion called a planetary nebula, and leaving behind their dense, hot, compressed cores. These remnant cores are called white dwarfs. More massive stars die more violently in the cataclysm of a supernova and leave behind even denser objects, neutron stars. And the most massive stars collapse completely, leaving behind black holes, which are cold in a very different sense, but whose story is entangled with the ultimate cold of the universe's far future. White dwarfs are among the most common stellar remnants in the galaxy. Our Milky Way contains hundreds of billions of them, though most are too faint to see except in our immediate neighbourhood. A typical white dwarf has a mass roughly similar to the Sun's, compressed into a volume roughly similar to Earth's. It is extraordinarily dense. A teaspoon of white dwarf material would weigh about 5 tons on Earth, but no longer undergoing fusion. It has no internal heat source. All it has is the residual thermal energy left over from its active life as a star. That energy radiates, away slowly, over billions of years. A newly formed white dwarf, still hot from the gravitational compression of its formation, shines with a surface temperature of perhaps 100,000 Kelvin or more, blazing blue-white, fierce and luminous. Over the following billions of years, it radiates that energy into space, cooling. Its surface temperature drops toward tens of thousands of Kelvin, then tens of thousands more millennia later, then lower still. Its color shifts from blue-white to yellow to orange to red, like a coal pulled from a fire and left to cool in the night air. This cooling process is extraordinarily slow. In the current age of the universe, about 13.8 billion years, even the oldest white dwarfs, those that formed in the very earliest epochs of stellar evolution, have only cooled to about 3,500 to 4,000 Kelvin, still warm enough to glow faintly in visible light, still far from the fate that awaits them. The theoretical end state of a white dwarf, if it cools long enough without any source of new heat or material, is called a black dwarf. A black dwarf is a white dwarf that has cooled completely to a temperature indistinguishable from the surrounding space, emitting no light, invisible except by its gravitational influence. A cold, dark, crystalline sphere, because as white dwarfs cool to very low temperatures, their carbon and oxygen interiors are expected to crystallize, like a diamond, the atoms locking into a rigid lattice as thermal motion falls too low to keep them fluid. Here is the remarkable thing. There are currently no black dwarfs in the universe. The universe is not old enough. The cooling process takes so much longer than the current age of the cosmos that even the oldest white dwarfs are still radiating heat, still detectable with sufficiently sensitive instruments. The first black dwarfs will not form for trillions of years, long after the last stars have burned out, long after the age of stellar light has ended. Neutron stars begin their existence in a very different state. Born in the violent collapse of a massive star, a supernova that briefly outshines an entire galaxy, a newborn neutron star has a surface temperature of perhaps 100 billion to 1 trillion Kelvin in its first seconds of existence. The interior temperatures are even more extraordinary. This is not cold. This is as hot as the universe gets in natural objects today. But neutron stars cool quickly at first, losing energy through intense neutrino emission, ghostly particles that carry away energy at a remarkable rate from the hot, dense interior. Within a few years, a neutron star's surface temperature drops from those extreme values to a few million Kelvin. Within tens of thousands of years, it has cooled to about 1 million Kelvin. Over millions and then billions of years, it continues to cool, dropping toward temperatures where it emits only X-rays, then infrared, then eventually nothing detectable, like white. Dwarfs, neutron stars in the very far future will cool toward the background temperature of space. They will become cold, dark, extraordinarily dense objects, spheres of neutron matter about the size of a city, with the mass of 1.5 suns radiating nothing, like the universe's most exotic stones. Both white dwarfs and neutron stars are already cold by many standards. The coolest known white dwarfs, the oldest and most faded, have surface temperatures of only a few thousand Kelvin. They glow faintly red, dim and aged, the embers of stars. In the future they will be dimmer still. The universe is full of these cooling stellar corpses, slowly surrendering their heat to the surrounding space, slowly approaching the cold that space itself maintains. The poet of the universe might call them elders, structures that have burned and exploded and formed and lost their companions and cooled. Patient across geological timescales, slowly dimming into the dark, there is something quietly beautiful about the image of a white dwarf, 3 billion years old, still glowing faintly red in the interstellar night, a dying ember of a star that once shone as brightly as the sun, now radiating the last of its ancient warmth into the void around it. It is cooling, slowly, inevitably, but still cooling, still connected to the warmth of its long-ago birth, still, in its own way, alive. So far, everything we have talked about, nebulae, molecular clouds, cosmic voids, rogue planets, stellar remnants, these are all forms of ordinary matter. They are made of protons, neutrons, and electrons, the familiar building blocks of the world. They can be detected with telescopes, measured in temperature, studied with instruments. They are cold, some of them extraordinarily cold, but they are part of the familiar universe of light and matter. But there is another universe layered over and through the one we can see, a universe of invisible, unknown stuff that we have never directly detected, that has no temperature in the ordinary sense, and that constitutes the overwhelming majority of the mass and energy in the cosmos. This is the universe of dark matter and dark energy. The existence of dark matter was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who noticed that the galaxies in the Coma cluster were moving much too fast to be held together by the gravitational pull of the visible matter alone. The cluster should have flown apart, the galaxies moving too fast for gravity to hold them, but they didn't. Something unseen was providing additional gravity, enough to hold the cluster together. Zwicky called it Dunkel Materie, dark matter. The evidence for dark matter has become overwhelming since then. The rotation curves of galaxies, the way stars at different distances from the galactic center orbit at different speeds, are inconsistent with the distribution of visible matter. Stars at the edges of galaxies orbit almost as fast as stars near the center, when they should be orbiting much more slowly if only visible matter were present. Something invisible provides additional gravitational mass throughout the outer regions of galaxies and their halos. Dark matter is also essential to explain how the large-scale structure of the universe formed as quickly as it did. The tiny density fluctuations in the early universe, those ripples in the CMB, should not have been able to grow into galaxies and clusters within the 13.8 billion year history of the universe using only ordinary matter. There simply wasn't enough time. Dark matter, which began clustering under gravity even before ordinary matter was free to do so, provided the gravitational scaffolding within which ordinary matter later collapsed to form the structures we see today. Without dark matter, there would be no galaxies. What is dark matter? That is one of the greatest open questions in all of science. We know what it is not. It is not ordinary. Protons and neutrons, not stars too dim to see. Not black holes, not in sufficient numbers anyway. Not antimatter. It does not emit, absorb, or scatter light. It interacts with ordinary matter only through gravity, and there is roughly 5 times as much of it in the universe as there is ordinary matter. 5 times as much of the invisible kind as of the kind everything we can see is made of. Dark energy is even more mysterious. Discovered in 1998, when 2 independent teams of astronomers studying the brightness of distant supernovae found that the expansion of the universe is accelerating, dark energy is an energy associated with empty space itself, a kind of intrinsic pressure or tension of the vacuum that pushes the universe to expand faster and faster over time. It constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. All the ordinary matter, everything you have ever seen, every planet, star, galaxy, nebula, constitutes only about 5%. Dark matter and dark energy have temperature only in the loosest sense. Dark matter, whatever it is almost certainly not like ordinary gas with a temperature reflecting the random motion of its particles in an ordinary way. The candidates most favoured by physicists, various hypothetical particles like WIMPs, axions, or sterile neutrinos, would exist at extremely low effective temperatures, having long since cooled from whatever energies they had in the early universe. Some dark matter candidates, like cold dark matter particles, are thought to move very slowly relative to the speed of light. Cold in the cosmological sense, meaning their thermal velocities are small compared to their bulk velocities. Dark energy is different still. It is associated with the vacuum energy of space, a property of the geometry of space-time itself, rather than a substance with particles and temperatures. It is cold in the sense of being an energy that does not concentrate, does not flow, does not produce heat in the way ordinary matter does. It is the energy of nothing, spread uniformly through the universe, driving its expansion. The interplay of dark matter and dark energy will determine the ultimate fate of the universe, and therefore the ultimate temperature it reaches. If dark energy remains what it currently appears to be, a constant energy density of the vacuum, then it will continue to drive the expansion of the universe at an accelerating rate forever. The universe will grow and grow and grow, its galaxies spreading ever farther apart, its average temperature dropping ever closer to absolute zero. This leads eventually to the heat death, or big freeze, which we will discuss in the final section of our journey. But some theoretical models allow dark energy to change over time, either growing stronger, which could lead to the Big Rip, a scenario in which dark energy eventually tears apart not just galaxies and star systems but atoms themselves, or growing weaker, which could allow gravity to eventually halt the expansion and reverse it, leading to a big crunch. For now, the dark universe sits unseen around us, its temperature undetectable, its nature unknown, its presence revealed only by the gravitational effects it has on the ordinary matter we can observe, the invisible scaffolding of the cosmos, cold and dark and everywhere. There is something remarkable about the fact that human beings, fragile, warm-blooded creatures living on a rocky planet orbiting a middle-aged star, have managed to create in their laboratories temperatures colder than the coldest naturally occurring places in the known universe. Not just slightly colder either. We have made things tens of billions of times colder than the ambient temperature of space. This achievement is the product of one of the most inventive and painstaking branches of experimental physics, the science of ultra-low temperature research, sometimes called cryogenics or ultra-cold physics. It required decades of work, multiple generations of scientists, Nobel Prizes, ingenious engineering, and a profound dedication to the art of making things be still. The story of how humans first approached absolute zero is a long one. In the 19th century, physicists were discovering that gases could be liquefied by cooling them under pressure, that air, which seemed so obviously gaseous, could be turned into a liquid at low enough temperatures. The race to liquefy gases, each colder than the last, drove rapid progress. Nitrogen liquefies at 77 Kelvin, hydrogen liquefies at 20 Kelvin. Helium, the last gas to be liquefied, was first brought to liquid form in 1908 by the Dutch physicist Heike Kamerlingh-Onnes at the University of Leiden, reaching a temperature of about 4 Kelvin. Kamerlingh-Onnes received the Nobel Prize in Physics for this work in 1913. But getting below the temperature of liquid helium required new techniques. Simple cooling by contact with a cold substance could only take you so far. To reach temperatures below about 1 Kelvin, physicists developed methods that use the quantum mechanical properties of matter itself. One crucial technique is called adiabatic demagnetization. Certain magnetic materials, when placed in a strong magnetic field, align their atomic magnetic moments in an ordered state. When the field is then slowly reduced, while the material is thermally isolated, the magnetic moments randomize again, and in doing so they extract thermal energy from the material, cooling it. This technique can reach temperatures in the millikelvin range, thousandths of a degree above absolute zero. An even more powerful variant uses the nuclear magnetic moments of individual atomic nuclei, rather than the overall electronic magnetic moments of the material. Nuclear adiabatic demagnetization can reach temperatures in the microkelvin range, millionths of a degree above absolute zero, and even into the picokelvin range in nuclear spins. In 2000, researchers at the Helsinki University of Technology's low-temperature laboratory reported nuclear spin temperatures below 100 picokelvin, 100 trillionths of a degree above absolute zero, using this technique. But the most celebrated achievements in ultra-low temperature physics came from laser cooling and magneto-optical traps. These techniques use the momentum of light, photons, to slow down atoms. When an atom absorbs a photon, it receives a tiny kick in the opposite direction. By carefully tuning laser beams to the right frequency, and pointing them at a cloud of atoms from all directions, physicists can bombard the atoms with photons in such a way that each photon kick slows the atom down slightly, regardless of which direction it is moving. The atoms are slowed, cooled, by the light itself. Laser cooling can bring a gas of atoms to temperatures in the microkelvin range, making them cold enough to trap in a magnetic trap for further cooling. Then, through a technique called evaporative cooling, allowing the fastest, hottest atoms to escape the trap while retaining the slower, colder ones, the temperature can be pushed lower still, into the nanokelvin range. This is how Bose-Einstein condensates are made, and this is how the temperature records we discussed earlier were set. Eric Cornell and Carl Wieman created the first Bose-Einstein condensate in 1995 at a temperature of about 170 nanokelvin, 170 billionths of a degree above absolute zero. Wolfgang Ketterle and his team at MIT pushed to 500 picokelvin in 2003, and in 2021, Ernst Rasel and his team at Leibniz University, using the Bremen drop tower, achieved 38 picokelvin, 38 trillionths of a degree above absolute zero, in a freely falling Bose-Einstein condensate. Each of these achievements required extraordinary ingenuity. At temperatures of 38 picokelvin, atoms move so slowly that an ordinary container would be ruinously hot by comparison. Any physical wall would instantly heat the ultra-cold atoms to billions of times their achieved temperature. So instead, the atoms are confined in magnetic traps, cages of magnetic field lines that repel the atoms without ever physically touching them. The atoms float in these invisible cages, suspended and isolated, almost perfectly still. NASA took this technology into space when it launched the Cold Atom Laboratory to the International Space Station in 2018. In orbit, away from Earth's gravity, the magnetic traps can confine atoms for much longer periods without the atoms falling away. The Cold Atom Lab regularly produces Bose-Einstein condensates in the microgravity environment of the ISS, achieving temperatures in the picokelvin range and allowing scientists to study the quantum behavior of ultra-cold matter in ways that are simply not possible on the ground. What do you learn from such extraordinary experiments? A great deal, it turns out. At ultra-low temperatures, phenomena emerge that are completely hidden at ordinary temperatures. Superconductivity, the ability of certain materials to conduct electricity with absolutely zero resistance, occurs in many materials only below a critical temperature. Some materials become superfluid, a state in which a liquid flows with zero viscosity, creeping up the walls of its container and seemingly defying gravity, moving through microscopic pores that would stop any ordinary fluid. These phenomena reveal deep truths about the quantum nature of matter, about how particles cooperate and coordinate their behavior when thermal chaos is eliminated. Ultracold atoms are also extraordinarily precise tools for measurement. The atomic clocks that define the international standard of time, the GPS satellites overhead, the synchronization of the internet, the precision of financial transactions are based on the resonance frequencies of atoms cooled to very low temperatures. Ultra-cold atoms also provide new ways to measure gravity with exquisite precision, potentially detecting gravitational waves from a different direction than LIGO, probing the fundamental constants of nature, and testing general relativity in new regimes. The quest for absolute zero has yielded not just records and curiosities, but practical knowledge that shapes the modern world. And at its heart, it has been a quest to understand what matter really is, to strip away the noise and thermal chaos of ordinary existence, and see the underlying quantum architecture of the universe laid bare. The coldest places ever created exist in small laboratories on Earth, maintained for fractions of a second, sustained by the patience and precision of human scientists. In those brief, extraordinary moments, matter enters states that no natural process in the universe has matched. The humans who made those temperatures are among the most remarkable explorers in history, not explorers of space, but explorers of cold, navigators of the last few degrees above absolute zero. When you get close enough to absolute zero, when you strip away enough thermal energy that the random motion of atoms becomes negligible, something extraordinary happens. The quantum mechanical nature of matter, normally hidden beneath the thermal chaos of everyday temperatures, emerges and takes over. The rules change. Things that should not be possible become not just possible but inevitable. To understand why, you need to know a little about what quantum mechanics says about particles. In the quantum world, particles are not simply tiny balls moving along precise trajectories. They are described by wave functions, mathematical objects that spread out in space, describing not where a particle definitely is, but rather the probability of finding it in various places. In ordinary, warm matter, this wave nature is completely hidden beneath the thermal chaos. Every particle is bouncing around so energetically and randomly that its quantum wave nature is averaged out. The world behaves classically. But as you cool matter toward absolute zero, as you remove more and more thermal energy, the particles slow down. Their wavelengths grow, and quantum mechanics' slower particles have longer wavelengths, and as atoms slow towards stillness, their quantum waves begin to extend over larger regions of space. At some critical temperature, something remarkable happens. The quantum waves of adjacent particles begin to overlap. They can no longer be treated as independent entities. They begin to merge into a collective quantum state. This is the physical basis of the Bose-Einstein condensate. In a BEC, the quantum waves of all the atoms, sometimes millions or even billions of them, overlap completely and merge into a single, shared wave function. The collection of atoms behaves as if it were one single quantum entity, a superatom, with all its parts marching in lockstep. In a Bose-Einstein condensate, atoms can be made to behave as waves in the most vivid and directly observable sense. They can interfere with each other, like ripples on a pond interfering when they meet, creating patterns of peaks and troughs. They can be split and then recombined, interfering with themselves in ways that encode information about the forces they have passed through. This is the basis of atom interferometry, a technique that uses the wave nature of cold atoms to make measurements of extraordinary precision. BECs also exhibit superfluidity, flowing without any viscosity whatsoever. Pour an ordinary liquid like water into a container, and it flows and sloshes and eventually comes to rest as friction dissipates its energy. But pour a superfluid into a container, and it will flow without ever losing energy to friction. It will creep up the walls of its container, up and over the edge and out the other side in a rotating bucket. In a superfluid will develop tiny rotating vortices that can persist indefinitely, unlike the vortices in ordinary fluids which dissipate and vanish. The superfluid has no mechanism for losing energy to friction, because the quantum coherence of its atoms prevents the random energy exchanges that create friction in ordinary matter. Superconductivity is the electrical analogue of superfluidity. In certain metals and compounds cooled below a critical temperature, electrons form pairs, called Cooper pairs, that move through the metal without any resistance. Electrical resistance in ordinary metals arises because electrons scatter off imperfections and thermal vibrations in the crystal lattice. But Cooper pairs move as a coherent quantum entity, and that coherence protects them from scattering. The result is that electricity can flow through a superconducting wire without any loss of energy whatsoever, indefinitely. Superconductivity is already central to modern technology. The powerful magnets in MRI machines, the devices that allow doctors to image the soft tissues of the human body without surgery, are made of superconducting wire cooled with liquid helium. The magnets in particle accelerators like the Large Hadron Collider at CERN, which accelerate protons to nearly the speed of light to study the fundamental particles of nature, are also superconducting. The discovery of new materials that superconduct at higher temperatures, ideally at room temperature, would be transformative, allowing lossless electrical transmission across power grids, ultra-powerful magnets for fusion reactors, and a host of other applications. There is another quantum phenomenon that emerges near absolute zero that deserves special mention: quantum tunneling. In quantum mechanics, particles can pass through energy barriers that classical physics says they should not be able to penetrate, like a ball rolling through a wall instead of bouncing off it. At ordinary temperatures, this effect is present but negligible for most purposes, overwhelmed by the thermal energy that allows particles to simply bounce over barriers rather than tunnel through them. But at very low temperatures, when thermal energy is nearly absent, quantum tunneling becomes the dominant mechanism for many physical processes. This has deep implications for the far future of the universe. White dwarfs in the universe's distant future, we mentioned earlier, may slowly decay through quantum tunneling processes, protons and neutrons in their crystalline interiors tunneling through energy barriers, rearranging over timescales of 10 to the 38th years or more. Even in the coldest future of the universe, quantum mechanics ensures that nothing is ever completely static. The Heisenberg uncertainty principle, which says that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa, means that particles at absolute zero would still possess what is called zero-point energy, a minimum residual motion that cannot be removed. This zero-point energy is the quantum mechanical reason why absolute zero is unreachable. Even if you removed all the thermal energy from a system, the quantum mechanical ground state energy, the zero-point energy, would remain. The particles would still possess some minimum energy, some irreducible quantum jitter, that cannot be extracted without violating the uncertainty principle. True absolute zero, perfect stillness, zero energy, is forbidden by the deepest laws of quantum mechanics. The universe cannot reach absolute zero for the same reason that you cannot know both the exact position and the exact momentum of a particle at the same time. It is not a limitation of technology. It is a fundamental property of reality. The floor is real. But even on the floor, there is still vibration. Even at the very bottom of temperature, the universe hums. There is something almost comforting about that. The cold can approach absolute zero, asymptotically, forever. But perfect stillness is never reached. The quantum world is always in motion, however faint that motion may be, even in the coldest places in the universe, even in the far future when the stars have long gone dark. The faint hum of zero-point energy persists. Something, somewhere, is always happening. We have travelled through the coldest places the universe contains today, but to complete this journey, we need to look forward, much further forward than human history, further forward than the age of the solar system, further forward than the current lifespan of the stars. We need to look to the far future of the cosmos, to the epochs that lie billions and then trillions and then unimaginable spans of years ahead. Because the universe, as it stands today, is not yet as cold as it will become. We live in a remarkably active, warm, luminous epoch, the age of stars, and that age, though it has already lasted 13.8 billion years, will eventually come to an end, and what follows will be colder and darker and quieter than anything we have explored tonight. The key fact about the future of the universe is that it is expanding. The space between galaxies is growing, driven by the mysterious dark energy embedded in the fabric of the cosmos. As space expands, two things happen. The galaxies recede from each other, and the cosmic microwave background continues to cool and redshift, its photons stretching to longer and longer wavelengths with less and less energy. In approximately 2 billion years, the Sun will begin to run out of hydrogen in its core, and will enter its red giant phase, swelling outward to engulf Mercury and Venus, and very likely Earth itself. This is our own local future. Warm, yes, but devastating for the only planet we know to host life. The outer solar system's worlds may briefly thaw as the expanded luminous Sun radiates energy across greater distances, but the inner solar system will be sterilized. About 5 billion years from now, the Sun will shed its outer layers as a planetary nebula, and its core will become the white dwarf it is destined to be. The solar system will then enter a quiet phase, a dim white dwarf at the center, slowly cooling, surrounded by frozen outer planets, Neptune, Uranus, perhaps others, locked in ice at temperatures below 100 Kelvin, in perpetual darkness as the dim remnant of the Sun provides only a fraction of its current energy. On larger scales, within about 100 million years, the expansion of the universe will carry distant galaxies beyond the cosmological horizon, the distance beyond which light can never reach us, because the expansion of space carries them away faster than light can travel. The galaxies outside our local group, the Milky Way, Andromeda, and their companions, will disappear from our observable universe. Astronomers living in the far future will look out at a sky in which only the galaxies of our merged local group are visible. The universe will appear much smaller and much quieter. About 100 billion years from now, roughly 7 times the current age of the universe, the Milky Way and Andromeda will have completed their merger into a single larger elliptical galaxy. Star formation will have slowed dramatically. The great spiral arms will be gone. The galaxy will be aging and settling. Then, roughly 1 to 100 trillion years from now, star formation will cease entirely. The supply of cold gas needed to form new stars will have been consumed, locked into existing stars and stellar remnants, or blown into intergalactic space by stellar winds and supernova. The last new stars will form. The age of stars, the stelliferous era, as some cosmologists call it, will draw to a close. For a time, the universe will still glow. The longest-lived stars, the dim, cool, red dwarfs that burn their hydrogen so slowly that they can shine for trillions of years, will continue their patient vigil, but they too will eventually exhaust their fuel and fade. The last red dwarf will probably burn out somewhere around 100 trillion years from now, 10,000 times the current age of the universe. After that, no new stars will form, and the existing ones will be dead. The universe will enter what is called the degenerate era, a vast epoch lasting from about 100 trillion years to 10 to the 40th power years or more. In this era, the universe will consist primarily of the remnants of dead stars, white dwarfs, neutron stars, and black holes. White dwarfs will be cooling, gradually over timescales of trillions of years, toward the background temperature of space, which will by then have dropped far below the current 2.725 Kelvin. The universe will be cold and dark and quiet. The CMB, stretched by billions of years of additional expansion, will have cooled to temperatures far below a millikelvin. The universe's ambient temperature will be approaching absolute zero, though never quite reaching it. Occasional events will punctuate the darkness. Rogue planets and brown dwarfs, those failed stars too small to have ignited fusion, will sometimes collide with each other, or with white dwarfs. Two merging white dwarfs might briefly explode as a Type 1a supernova, a last flash of light in the long darkness. Neutron stars might collide, but these events will be separated by such vast spans of time that the universe between them will be essentially static, cold, dark, expanding, and quiet. Then, perhaps 10 to the 37th power to 10 to the 40th power years from now, if protons decay, which physics predicts they might, though it has not been observed, ordinary matter itself will begin to disintegrate. Protons and neutrons will slowly decay into lighter particles, positrons, photons, neutrinos, over timescales so enormous that they strain all human comprehension. The white dwarfs and neutron stars will slowly evaporate into radiation. Even the remnant planets and asteroids will disintegrate. By 10 to the 40th power years from now, ordinary matter may no longer exist. Black holes will dominate this era. They are the most durable objects in the universe, sustained by the extreme curvature of space-time rather than by any ordinary matter structure. But even black holes are not eternal. Stephen Hawking showed in 1974 that black holes slowly radiate energy through a quantum mechanical process at their event horizons, what is now called Hawking radiation. Over an extraordinarily long time, a black hole loses mass and energy through this radiation, shrinking until it finally evaporates completely in a brief burst of energy. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate through Hawking radiation. A supermassive black hole, 1 billion times the mass of the Sun, would take about 10 to the 99th power years or more. In a universe at 10 to the 100th power years, even the most massive black holes will have evaporated. What remains? After the black holes are gone, after ordinary matter has decayed, after all the light from the evaporating black holes has been stretched by expansion to wavelengths so long they carry almost no energy at all, the universe will consist of an extraordinarily dilute gas of photons, neutrinos, electrons, positrons, and a scattering of other particles, all widely separated, all moving apart, the temperature of the whole cosmos asymptotically approaching, but never quite reaching absolute zero. This is the heat death. This is the big freeze, the ultimate cold of the universe's final state. The name is paradoxical. Heat death suggests something hot, but it refers instead to the thermodynamic concept of entropy, the idea that the universe reaches a state of maximum entropy, in which all energy is uniformly distributed and no more work can be done. No temperature differences remain large, enough to drive any process. No stars burn, no life is possible, no information can be processed, no thought can occur. The universe settles into an eternal, cold, featureless equilibrium, and yet, the quantum mechanical hum of zero-point energy persists. The universe, even in its final state, is not truly at absolute zero. The floor of all temperatures is forever approached but never touched. In the darkest, coldest, most final state of the universe, there is still, somewhere, some irreducible minimum vibration, some faint quantum jitter, some memory of energy. It is not comforting in the ordinary sense. The heat death lies so far in the future that the distance is not just incomprehensible, it is actively meaningless to our ordinary experience of time. The current age of the universe, 13.8 billion years, is an eye blink compared to the timescale of the degenerate era. The degenerate era is a whisper compared to the age of the black hole era, and the black hole era is barely a beginning compared to the time that follows. We live in the warmest, brightest, most active era the universe will ever know. The age of stars is the youth of the cosmos. The epochs of cold and darkness that follow will last so much longer than the current age of stars that our entire stelliferous era, every galaxy, every star, every moment of warmth and light is a brief, extraordinary dawn before an infinite winter. But that winter has not come. The stars still burn. The molecular clouds still form new suns. The rogue planets still drift through the warmish bath of the cosmic microwave background. The Boomerang Nebula still blows its extraordinary cold breath into the space around it, and here, on this planet, in this room, you are warm. You're radiating heat into the space around you. The iron in your blood, forged in the heart of a dying star billions of years ago, still carries the warmth of its cosmic origin. The oxygen in every breath was shaped by the nuclear fires of ancient suns. You're not just a witness to the warmth of the universe's active era. You're a product of it. You're made of the warmth of the stars. The cold of the universe is vast and deep and eventually absolute. But right now, in this moment, in this quiet room as you drift towards sleep, you are warm. Impossibly, improbably, miraculously warm. We have travelled far tonight. We began at the concept of absolute zero, the lowest temperature in principle, a floor that cannot quite be touched. We visited the Boomerang Nebula, 5,000 light-years away, 1 degree above absolute zero, the coldest natural place in the known universe, a dying star's last frigid breath. We drifted through the cold nurseries of molecular clouds, where temperatures hover near 10 Kelvin and stars are born from the slow collapse of dark, frigid gas. We felt the faint, even warmth of the cosmic microwave background, that ancient whisper from the Big Bang itself, 2.725 Kelvin filling every corner of the universe equally. We floated through the vast, nearly empty cosmic voids, where the only temperature is that background glow, and where the universe is mostly made of nothing. We imagined the rogue planets drifting alone through the dark, their surfaces frozen near absolute zero, their interiors perhaps quietly warm. We traced the long, slow cooling of white dwarfs and neutron stars, stellar corpses fading over billions of years toward the cold of surrounding space. We glimpsed the dark matter halo that surrounds the galaxy, invisible and cold, its nature still unknown. We visited the laboratories where humans have achieved temperatures of 38 trillionths of a degree above absolute zero, colder than anywhere else in the universe, made cold by patient, ingenious science. We saw the strange and beautiful quantum world that emerges at those temperatures, and we look to the far future, when the last stars have burned and the universe slowly settles toward its final cold. What is the meaning of all this cold? One answer is that the cold is the universe's resting state, what it returns to inevitably when energy is no longer being added and the entropy of the cosmos has reached its maximum. The stars and the warmth they provide are temporary disturbances in an ocean of cold, brief, brilliant exceptions to a background of near absolute quiet that pervades most of space and most of cosmic time. Another answer is that the cold is not an ending but a setting, the backdrop against which the universe's most interesting structures form. The molecular clouds are cold and stars are born from them. The cosmic voids are cold, and they define the structure of the cosmic web that holds galaxies in place. The cosmic microwave background is cold, and within its tiny temperature variations is written the complete story of cosmic structure formation. Even in the laboratory, the extreme cold of a Bose-Einstein condensate reveals quantum truths that transform our understanding of matter and energy. The cold is not nothing. The cold is the stage. And you, right here, right now, are a warm body in a cold universe made of star stuff, carrying the heat of ancient suns in every cell, resting in a brief and extraordinary moment when the cosmos is alive with light and warmth and complexity. You are not here by accident. You are here because the universe, in the warm middle portion of its existence, found conditions precisely right to form you. A being capable of wondering about the cold that surrounds you, capable of being moved by the thought of a star's dying breath cooling the space around it to 1 Kelvin, capable of feeling something like peace at the idea of an eternal, quiet cold waiting patiently at the end of all things. The Boomerang Nebula glows faintly in the direction of Centaurus right now, 5,000 light-years away, impossibly cold, impossibly beautiful. The molecular cloud nurseries of the Milky Way drift, in darkness, gathering the material of future stars in their cold cores. The cosmic voids expand, empty and silent. The rogue planets drift. The white dwarfs fade. The background radiation cools, imperceptibly over billions of years, toward the floor it will never quite touch. And you, here, resting. You are warm in a cold universe. You are awake in an indifferent dark. You are complex in a cosmos that trends towards simplicity and quiet. That is not a reason for despair. It is a reason for wonder. Every thought you have, every feeling, every moment of beauty or curiosity or connection, these are gifts of the warm era. They happen now, in the brightest and most active chapter of cosmic history. They happen in you, made of the same matter as the stars, warmed by the same type of nuclear fire that lights every sun in the galaxy. The cold will come eventually to all things, but not now, not yet. The stars are still burning, the universe is still alive, and you, in this quiet room, are still warm. Let your breathing slow. Let your thoughts thin and drift. The Milky Way is turning overhead, invisible through the ceiling but real and vast and ancient. The cosmic microwave background is streaming through the walls, carrying its message from the dawn of time. Somewhere out there, a rogue planet is drifting in the dark. Let's linger a little longer on the concept of absolute zero, because it is so central to everything else we've discussed tonight. Understanding why 0 Kelvin cannot be reached, truly understanding it, not just accepting the statement, opens a door into one of the most elegant and counterintuitive areas of physics. Thermodynamics, the branch of physics that deals with heat and temperature, rests on 4 laws. They are numbered 0 through 3, which is a quirk of history. The 0th law was added after the others were already established, because it was so fundamental it logically had to come first. The 3rd law is the one that tells us about absolute zero. In one of its formulations, it states that the entropy, the disorder, the number of possible ways a system can be arranged, of a perfect crystal approaches a defined minimum value as temperature approaches 0 Kelvin. That minimum is not necessarily zero entropy, but it is a fixed, determined constant for any given system. And the crucial implication of this is that to actually reach absolute zero, you would need to remove that last fixed residual entropy. But to remove entropy from a system, you need to perform work on it. You need to cool it using something even colder. And to have something even colder, you need to cool that something with something colder still. This chain never ends. No finite series of steps can remove all entropy from a system. The 3rd law is not merely a practical inconvenience. It is a fundamental fact about the architecture of energy and disorder in the universe. There is another way to see why absolute zero is unreachable, and this one involves quantum mechanics directly. According to the Heisenberg uncertainty principle, the more precisely you know the momentum of a particle, the more you've constrained how fast it is moving, the less precisely you can know its position, and vice versa. This is not a matter of measurement technique. It is a fundamental property of nature. Particles do not have definite positions and momenta simultaneously. They exist in quantum superpositions. Now, at absolute zero, a particle would have zero energy, which means zero momentum, which means we would know its momentum exactly. It would be precisely zero. But the Heisenberg uncertainty principle says that if momentum is known exactly, position is completely unknown. And if position is completely unknown, the particle could be anywhere in the universe. That is physically impossible for a particle sitting in a material object. Therefore, particles in a material object cannot have exactly zero momentum. They must always retain some residual quantum motion, the 0-point energy, which corresponds to a temperature that is greater than absolute zero. This 0-point energy is not just a theoretical construct, it has measurable effects. Liquid helium, uniquely among all substances, remains liquid at atmospheric pressure down to absolute zero. It never solidifies no matter how cold you make it, precisely because the 0-point energy of its atoms is large enough to keep them too agitated to lock into a crystal. You have to apply pressure to force helium to solidify, overcoming the 0-point motion with external force. Liquid helium is a direct demonstration that absolute zero is physically unreachable. The quantum mechanics of helium atoms prevents them from crystallizing simply through cooling. The concept of 0-point energy also has cosmological significance. The vacuum of space, empty space containing no particles, still contains energy, the so-called vacuum energy or cosmological constant, which is thought to be related to the 0-point fluctuations of quantum fields. This vacuum energy is the leading candidate for dark energy, the mysterious force driving the acceleration of the universe's expansion. In other words, the quantum mechanical reason why absolute zero is unreachable may be connected to the quantum mechanical reason why the universe will expand forever. The cold of the universe and its ultimate expansion are woven together in the deepest laws of quantum mechanics and thermodynamics. The flaw of temperature and the fate of the cosmos are, in a sense, the same story told from two different directions. As you rest tonight, let that idea hum at the edge of your thoughts. The universe is cold, it is getting colder, but there is a flaw it cannot quite reach. And the reason it cannot quite reach that flaw is the same reason that matter exists in all its complex forms, the same reason that stars and planets and molecules and life are possible at all. Because quantum mechanics imposes a minimum on motion, a flaw on stillness, a residual vibration in the very fabric of everything. The cold cannot have the last word. The quantum world will always hum, however faintly. Before we leave the cosmic microwave background behind, there is one more thing worth dwelling on, an anomaly so large and so puzzling that it has been the subject of intense scientific debate for decades. It is called, simply, the cold spot, and it is one of the most intriguing unsolved mysteries in cosmology. In 2004, astronomers analysing data from NASA's WMAP satellite noticed an unusually large and unusually cold region in the microwave sky, located in the direction of the constellation Eridanus. The cold spot, as it quickly became known, is roughly 70 microkelvin colder than the surrounding CMB temperature. That might sound like a tiny difference, but in the context of the CMB's exquisitely uniform temperature, it is an enormous anomaly, many times larger than the typical temperature fluctuations that statistical models predict. What makes the cold spot particularly interesting is not just its size, but also its sheer scale. It spans roughly 10 degrees on the sky, about 20 times the apparent diameter of the full moon. For something to produce a cold region of that angular size in the CMB requires either an extremely large structure along the line of sight or some exotic physical process in the early universe. The most mundane explanation, and often in science, the mundane explanation turns out to be correct, is that the cold spot is caused by a supervoid, a region of space between us and the CMB surface that is unusually devoid of matter. As we discussed earlier, photons passing through a void lose a little energy through the integrated Sachs-Wolf effect. A very large, very empty void could produce exactly the kind of cold region we observe. In 2015, a team led by Istvan Sapudi at the University of Hawaii identified what appeared to be a supervoid about 150 to 300 megaparsecs across, located at a distance of about 3 billion light-years, roughly aligned with the cold spot. If this supervoid is real and as large as suggested, it could explain the temperature anomaly without invoking any unusual physics. However, the supervoid explanation is contested. Some calculations suggest that even this large supervoid would not be quite large enough, or quite empty enough, to produce the observed cooling. If the supervoid alone cannot explain the cold spot, something else must be contributing. The more exotic explanations proposed over the years include the influence of a cosmic texture, a topological defect in the fabric of space-time left over from a phase transition in the early universe, or even the collision of our universe with another universe in a multiverse scenario. That last idea, while speculative, has a certain breathtaking quality to it. The possibility that the most anomalous feature in our cosmic microwave background is the bruise left by a collision with an entirely separate universe, billions of years ago, before the CMB photons were even released. We don't know which explanation, if any, is correct. The cold spot remains an open question. Current and future CMB experiments, including the Simons Observatory and the proposed CMB Stage 4 experiment, will make more precise measurements of the region and hopefully reveal whether the supervoid explanation is sufficient, or whether something more exotic is required. But whatever the cause, the cold spot reminds us that the cosmic microwave background is not just a uniform, featureless haze. It is a richly textured record of the early universe and of the structures, seen and unseen, that light has passed through on its 13.8 billion-year journey to our detectors. Reading the CMB is like reading a palimpsest, a document written over and over with the original text still faintly visible, beneath the later additions. The cold spot may be the faint impression of something enormous and ancient, written into the oldest light in the universe, we have ranged far across the universe tonight, to nebulae and voids and the deep future. But let's come a little closer to home for a moment, because the cold of our own solar system has its own remarkable story to tell. Right here, in the family of worlds orbiting our Sun, there are places so cold that they challenge our intuitions about temperature just as surely as the most extreme cosmic environments. Pluto, the dwarf planet at the edge of the solar system about 5.9 billion kilometers from the Sun on average, has a surface temperature of roughly 44 Kelvin, that is about negative 229 degrees Celsius, or negative 380 degrees Fahrenheit. On Pluto's surface, nitrogen, methane and carbon monoxide exist as ices, frozen solid at temperatures that would turn most of Earth's atmosphere into a liquid or a frost. When the new Horizon spacecraft flew past Pluto in 2015, it revealed a world of extraordinary beauty and geological complexity. Towering water ice mountains rising kilometers above nitrogen ice plains, a heart-shaped region called Tombor Regio, filled with smooth young nitrogen ice, and evidence of complex atmospheric chemistry driven by the thin haze of nitrogen and methane surrounding the dwarf planet. But Pluto is far from the coldest place in the solar system. That distinction belongs to the permanently shadowed craters near the lunar poles, where sunlight has never reached in billions of years, and where temperatures drop to about 26 Kelvin, negative 247 degrees Celsius. NASA's Lunar Reconnaissance Orbiter measured these temperatures in the south polar craters of the Moon and found them to be among the coldest surfaces in the solar system. In those permanently shadowed craters, water ice, delivered by comets and asteroids over billions of years and preserved in the perpetual dark, has accumulated in significant quantities. Future lunar explorers and settlers may one day mine this ice for water and rocket fuel. Even colder in some respects are the outer reaches of the solar system, the Kuiper Belt and the Oort cloud, where the sun's warmth is so diluted by distance that objects exist in permanent near-absolute cold. Sedna, a trans-Neptunian object discovered in 2003, orbits the Sun at distances ranging from 76 to 937 astronomical units, where 1 astronomical unit is the Earth-Sun distance. At those distances, the Sun is just a bright star. Sedna's surface temperature is approximately 12 Kelvin, negative 261 degrees Celsius, one of the coldest surfaces of any known solar system body. The Oort cloud, that vast spherical swarm of icy bodies at the very edge of the solar system, stretching from about 2,000 to 100,000 astronomical units from the Sun, is colder still. Objects in the outer Oort cloud receive almost no solar radiation whatsoever. Their temperatures are essentially indistinguishable from the ambient temperature of interstellar space, about 2.725 Kelvin, the cosmic microwave background temperature. They are warmed only by the faint ancient light that permeates the universe from every direction equally. In a sense, the outer Oort cloud is not truly part of the solar system in any warm sense. It is solar material, comets and icy bodies that formed around the Sun, but it exists in a thermal environment that is essentially indistinguishable from the open interstellar void. The boundary between our solar system and the cold of deep space is not a sharp line. It is a gradient, a slow fading of solar influence, a gradual surrender to the deep cold that pervades the rest of the galaxy. The Voyager spacecraft, those 2 remarkable ambassadors of humanity launched in 1977 and now travelling through interstellar space beyond the solar system, are experiencing something like this gradient right now. Voyager 1 is currently about 24 billion kilometers from the Sun, well beyond the heliopause, the boundary where the solar wind gives way to interstellar space. The temperature of the interstellar medium in that region is measured in thousands of Kelvin, but that refers to the energy of individual particles, not the thermal temperature in the familiar sense. The density of particles is so low that although each particle moves very fast, high temperature, there are so few of them that the total heat energy they could transfer to a spacecraft is negligible. The effective temperature that a thermometer would register is close to that of the CMB, just a few Kelvin. Our solar system is a warm island in a cold universe, and even within that island there are frozen shores where the warmth of our star barely reaches. The cold is always there, at the edges of the light, waiting. One detail we have not fully explored yet is the practical question of how scientists actually measure extreme cold. how they determine the temperature of a cloud of gas 5,000 light-years away, or verify that a laboratory experiment has achieved a temperature of 38 picokelvin. Because measuring temperature in these extreme conditions is not simply a matter of inserting a thermometer. At the most fundamental level, temperature is a measurement of the average kinetic energy of a system's particles, how fast they are moving on average. For an ordinary gas, you can measure temperature by placing a calibrated sensor, a thermometer, in contact with the gas and allowing the gas and the thermometer to reach thermal equilibrium. The thermometer changes in some measurable way. The height of a liquid column, the electrical resistance of a metal, the voltage across a junction, in proportion to its temperature. But for a gas cooled to a few picokelvin, you cannot place a thermometer in it. The thermometer itself would be at room temperature, about 300 Kelvin, and its contact with the ultra-cold gas would instantly heat the gas to billions of times its intended temperature. Instead, physicists use non-invasive optical methods. They take images of the expanding gas cloud using absorption imaging, shining a precisely calibrated laser through the cloud, and measuring how the absorption pattern changes as the cloud expands after release from its magnetic trap. The rate of expansion of the cloud is directly related to the thermal velocity of its atoms, which is directly related to its temperature. By measuring how slowly the cloud expands, physicists can determine the temperature with remarkable precision. For astronomical objects like the Boomerang Nebula, the technique is different. You cannot observe a gas cloud 5,000 light-years away with the same methods. Instead, astronomers use spectroscopy, the analysis of the light or radio waves emitted or absorbed by the cloud, to determine temperature. Different atomic and molecular transitions produce different frequencies of light, and the ratio of emission at different frequencies tells you the distribution of energies among the molecules, which directly gives you the temperature. For the Boomerang Nebula, astronomers were able to determine its temperature by observing how it absorbed the cosmic microwave background radiation at specific frequencies corresponding to transitions of carbon monoxide molecules. The absorption pattern was consistent only with a gas temperature below that of the CMB, below 2.725 Kelvin. For the CMB itself, temperature is measured with extraordinary sensitivity by instruments cooled with liquid helium and liquid nitrogen to temperatures just a few Kelvin. The detectors must be nearly as cold as what they are measuring, to avoid being overwhelmed by their own thermal noise. The Planck satellite's detectors were cooled to 0.1 Kelvin, 100 millikelvin above absolute zero, making them among the coldest operational objects ever launched into space. These ultra-cold detectors allowed Planck to measure CMB temperature fluctuations to the millionth of a degree level, revealing the fine structure of the universe's primordial density variations with unprecedented precision. The act of measuring temperature at these extremes is itself a remarkable achievement, a triumph of human ingenuity in the face of the universe's natural extremes. We cannot go to the Boomerang Nebula to confirm its temperature with a probe. We cannot insert a sensor into the cold core of a molecular cloud, but we can read the light and radio waves that these objects emit and absorb, and from those signatures, derive the temperatures with confidence. The universe speaks in frequencies, and we have learned to listen. As we draw close to the end of our journey, it is worth pausing to reflect on what we have actually learned, not just the facts about particular cold places, but what those cold places collectively teach us about the universe and our place in it. The cosmic microwave background at 2.725 Kelvin is a direct measurement of the age and evolution of the universe. Its temperature tells us how much the universe has expanded since the Big Bang, and the tiny fluctuations within it tell us the seeds from which all cosmic structure grew. Cold, in this case, is the universe's memory, the preserved record of its earliest moments. The molecular clouds at 10 to 30 Kelvin are where stars are born. Their coldness is the precondition for the existence of everything warm. The cold nurseries produce the hot stars that light the galaxies. Cold, in this case, is the source of warmth. The Boomerang Nebula, at 1 Kelvin, is a reminder that dying is creative. The extraordinary cold at the heart of this nebula is produced by the dying star's last exhalation, by the rapid expansion of its final shedding. The dying creates the cold, and the cold is extraordinary. Death in the universe is not an ending but a transformation. The cosmic voids, filling 80% of the universe's volume, are cold because they are empty, or nearly so, and yet they are not meaningless. They define the structure of the cosmic web. They are the spaces that make the filaments and walls of galaxies meaningful. The cold emptiness is the negative space of the cosmic masterwork. The rogue planets drifting at near CMB temperatures are cold because they are alone, cut off from the warmth of a parent star. And yet even the coldest rogue planet may harbour warmth in its interior, may potentially support life of a kind we have never imagined. Cold on the outside, perhaps warm within. Isolation does not necessarily mean lifelessness. The white dwarfs and neutron stars are cooling relics, the aftermath of stellar fire gradually surrendering their heat to the surrounding cold. They are already cold by many standards, and growing colder. They are the universe's way of storing the memory of stars long after the stars themselves have gone. The laboratory cold, 38 picokelvin achieved in a drop tower in Bremen, is the universe's cold turned back on itself. Human beings made of warm star stuff, learning to create cold more extreme than anything nature produces in order to understand the quantum architecture of matter and energy. The universe studies itself through its own children. And the heat death, the ultimate cold at the end of cosmic time, is not a failure or a tragedy. It is simply the final state of a system that has spent its entire existence in a magnificent extended process of cooling. The universe was born hot, incomprehensibly hot, in the first moments after the Big Bang. It has been cooling ever since. The cold at the end is simply the completion of a process that began with the first expansion, and that has produced along the way all the complexity and warmth and life and thought and wonder that the universe contains. Cold is not the enemy of life. Cold is the background against which life burns briefly and brightly before cooling back to the stillness from which it came. You are that life, warm briefly against the cold. Let that thought carry you gently into sleep. We have spent a great deal of time exploring how cold things are, but there is something deeply satisfying about also understanding how things become cold. The actual physical mechanisms by which energy drains away from matter into the surrounding void. Because cooling is not one process, it is many. And the way a star cools is different from the way a nebula cools, which is different from the way a laboratory sample cools, which is different from the way the universe as a whole cools. The most familiar mechanism of heat loss is thermal radiation. Every object with a temperature above absolute zero emits electromagnetic radiation. Light, in the broadest sense of that word, including infrared, visible, ultraviolet, X-rays, radio waves, depending on the temperature of the object. A human body at 37 degrees Celsius emits primarily in the infrared. A star's surface at 5,778 Kelvin emits most of its energy in the visible spectrum. A white dwarf at 100,000 Kelvin blazes in ultraviolet. The hotter the object, the shorter the peak wavelength of its emission. The rate at which an object radiates energy is proportional to the fourth power of its temperature, a law called the Stefan-Boltzmann law. This means that hotter objects radiate enormously more energy per unit area than cooler ones. Double an object's temperature, and it radiates 16 times as much energy per second. This is why stars cool slowly as they age, and their temperature drops. The cooler they become, the less energy they radiate, and therefore the longer it takes to cool further. The cooling process slows as it proceeds, asymptotically approaching equilibrium with the surrounding environment. In space, radiation is the dominant cooling mechanism for most astronomical objects, because there is nothing else for heat to flow into. No air, no water, no physical contact with cooler materials. A white dwarf floating in interstellar space radiates into the vacuum around it, and that radiation carries energy away at a rate determined entirely by its surface temperature and surface area. As the white dwarf cools, it radiates less, cools more slowly, and approaches but never quite reaches the ambient temperature of the surrounding space. Another crucial cooling mechanism in the universe is neutrino emission. Neutrinos are extraordinarily lightweight, electrically neutral particles that interact with matter so weakly that they can pass through a light year of lead without any interaction at all. Yet they carry energy, and in the incredibly hot, incredibly dense cores of stars and newly formed neutron stars, neutrino emission is the dominant mechanism by which energy escapes. In the core of a massive star in its dying moments, just before and during a supernova, the temperature reaches trillions of Kelvin and the density exceeds that of an atomic nucleus. At these conditions, nuclear reactions produce neutrinos in enormous quantities, and those neutrinos, despite their weak interactions, carry away energy so efficiently that they dominate the cooling. When supernova 1987A occurred in the Large Magellanic Cloud in February 1987, observatories around the world detected a burst of neutrinos that arrived a few hours before the optical brightening of the explosion. Approximately 10 to the power of 58 neutrinos were released by the collapsing core, carrying away more energy in a few seconds than the Sun radiates in 10 billion years. The core cooled from trillions of Kelvin to billions of Kelvin in those few seconds, primarily through neutrino emission. The expanding gas of the Boomerang Nebula cools through a completely different mechanism: adiabatic expansion. When a gas expands rapidly without exchanging heat with its surroundings, a process called adiabatic expansion. The work it does pushing against the surrounding medium comes at the expense of its own internal thermal energy. The gas cools as it expands, not by radiating energy away, though it does that too, but by converting thermal energy into the kinetic energy of bulk expansion. This is the same principle that makes a spray can feel cold when you press the button and release gas. The propellant gas expands as it flows through the nozzle, converting its internal thermal energy into the kinetic energy of the spray and cooling in the process. In the Boomerang Nebula, this process occurs on a grand scale. Gas ejected at 164 km per second from the dying central star expands adiabatically as it flows outward, and the temperature of the gas drops from whatever it was near the star's surface to approximately 1 Kelvin at the outer reaches of the outflow. The universe's most extreme adiabatic cooling creates the universe's coldest natural place. In laboratory settings, the primary cooling methods are laser cooling and evaporative cooling. Laser cooling works by using the momentum of light to slow atoms. Photons collide with atoms and push them in the direction opposite to their motion, selectively slowing atoms that are moving toward the laser source. By surrounding a gas cloud with laser beams from all directions, each tuned to the right frequency to interact with atoms moving toward them, a physicist can slow the atoms significantly. The process is limited, however, by quantum mechanics. Below a certain temperature called the Doppler cooling limit, atoms begin to emit and absorb photons in ways that no longer produce net cooling. Below the Doppler limit, physicists use other techniques. Sisyphus cooling, named after the mythological figure who was condemned to roll a boulder endlessly up a hill, exploits the internal energy structure of atoms in a way that forces them to continuously lose energy as they move through a spatially varying light field like a ball always rolling uphill. This can achieve temperatures below 1/1,000,000th of a Kelvin. For the final steps toward the coldest temperatures ever achieved, evaporative cooling takes over. Imagine a coffee cup. The hottest water molecules have enough energy to escape the surface as steam, carrying their high energy away with them and leaving the cooler molecules behind. The coffee, deprived of its hottest molecules, gets colder. The same principle, applied to a magnetically trapped cloud of ultra-cold atoms, allows physicists to selectively remove the most energetic atoms from the trap, leaving behind an ever-cooler sample. The process is self-limiting. As the cloud gets colder, fewer and fewer atoms have enough energy to escape, and the cooling slows. But with careful control of the trap parameters, temperatures in the nanokelvin to picokelvin range are achievable. Each of these cooling mechanisms, radiation, neutrino emission, adiabatic expansion, laser, cooling, evaporative cooling, is a different way of answering the same fundamental question. How does energy leave a system? The answers range from the sublimely cosmic, a dying star's core cooling through neutrino emission in seconds, to the exquisitely engineered, a cloud of rubidium atoms chilled to 38 picokelvin by lasers, magnetic fields, and the physics of a freefall drop. But they all obey the same underlying thermodynamics. Energy flows from more concentrated to less concentrated. Temperature gradients drive heat flows, and the universe, patient and relentless, eventually draws everything toward equilibrium. You too are losing heat right now. Your skin radiates infrared light into the cooler air and surfaces around you. Your breath carries warm, moist air away from your body. Your feet conduct heat into the mattress beneath you. You are in continuous thermal conversation with your environment, losing heat and gaining it back, maintaining your body temperature of 37 degrees Celsius through the continuous burning of glucose and fat in your cells. You are a thermal process, a warm, complex, conscious thermal process briefly maintaining your temperature against the cold that surrounds you. And that, in a universe where the natural state is cold and dark and still, is one of the most extraordinary things there is. Rest now. Let the universe be cold around you. You are warm enough.